Here, we're going to discuss two applications of Gaussian elimination. The first one is to determine whether a given factor is in the span of certain other factors. Let's look at this example. Okay, determine whether this factor 3 minus 2, 4 belong to the span of these two factors, 2 minus 1, 1 and minus 1, 3. So the way we're going to do is, okay, so suppose, well, let's suppose it is and see whether there's some disaster happen. So suppose 3 minus 2, 4 is really in the span, belongs to the span of these two factors. What does that mean? That means that this can be written as a linear combination of these two factors. Because what does span mean? Span, we learned it last week, is the collection of all the linear combination. And then saying that this factor belong to the span means that, okay, that means 3 minus 2, 4 equals to a linear combination. That means that, okay, it looks like this, alpha times 2 minus 1, 1, and then plus beta times minus 1, 1, 3. Okay? And then by equating the coordinates, okay, then we obtain a system of equation. The system of equation that we obtain has the form, so firstly, I have 3 equals to alpha times 2 plus beta times minus 1. So alpha times 2, so 2 alpha. And then minus beta. And then the second equation will be minus 2 equals to minus alpha plus beta. Right? Minus 2 equals minus alpha plus beta. The final equation is 4 equals to alpha plus 3 beta. Alpha plus 3 beta. Let me be consistent. I'm going to use red here as well. Okay? But then you realize that in this case, we obtain a system equation. So we can solve it by using Gaussian elimination. So in matrix form, the system equation equals to, we actually have to swap them, okay? So if I swap them correctly, then the equation is actually given by 2 minus 1, minus 1, 1, 1, 3, and then 3 minus 2, 4. And then now we conduct Gaussian elimination. The first way we do is try to make this entry become 1. The easiest way is to swap the first row and the third row, i.e. swap the first and third equation. So if I swap them, I get 1, 3, 4, and 2 minus 1, 3, and then minus 1, 1, minus 2. So I didn't do anything, I just swap the first row and the third row. And now let us conduct Gaussian elimination. So we want to kill this two entry here. So this entry is easy to kill. We simply add the first row to the second row. So I get 1, 3, 4. 1 add to minus 1 is 0. And the 3 add to 1, 4. And the 4 add to minus 2, you get 2. Okay? How about this entry here? How do I kill that? So I'm going to multiply 1 by minus 2. And then add it to 2, then I get 0. But then I need to multiply the entire row by minus 2. So this entry, 3 minus 2, become minus 6. Add it to minus 1, I get minus 7. And then finally, 4 times minus 2, minus 8, add 3, minus 5. So let me record here for your convenience, write down what I've done. So firstly, I add the first row to the second row. And also, I add the first row times -2, and I add it to the third row. Okay? To make upper triangular, the next entry that I have to kill is this entry here. So what I'm going to do is to multiply the second row, so be brave, okay? You just need to be brave, and then multiply the second row by 7/4, and then add it to the third row. So 1, 3, 4, and then this is unchanged, and then 0, and then 4 times 7/4, and then add it to -7, you get 0. Indeed, that's the purpose, okay? And then 2 times 7/4 is 7/2, and then 7/2 minus 5 is 7/2 minus 5. Well, you don't have to do it quickly, right? So you get something like this. So now, this is in upper triangular form, so we say we're done, REF. But what is so special about this system is when you look at the third equation, what I say, the third equation what does it say? It says that, okay, the left-hand side is 0 alpha plus 0 beta, obviously, it means 0, equals to 7/2 minus 5. Wait, is that possible? 0 equals to 3.5 minus 5. This is impossible. So this is indeed a contradiction, okay? Contradiction. So what does it contradict with? It contradicts with the assumption, suppose this factor is in the span of these two factors. So that means that this cannot happen. So hence 3 minus 2, 4 does not belong to the span of 2 minus 1, 1 and minus 1, 1, 3. Because if this belong to the span, and then using my calculation, I will have 0 equal to 7/2 minus 5, and this is clearly impossible. So this is an application of Gaussian elimination in determining whether a factor belongs to the span of other two factors, okay? You will see more examples like this in your homework question this week. Another application of Gaussian elimination is to solve a problem that we discussed last time. That is to find a basis of a subspace. So let me just remind you what subspace was. A subspace means it's a subset that is closed under addition and also closed under scalar multiplication. And here we have an example of subspace that is all the factors with 3 components, x1, x2, x3, such that it satisfies the coordinate satisfy 2 equations. The first equation is 2x1 plus x2 minus x3 equals 0. The other equation is x1 minus x2 plus x3 equals 0. So how do we find a basis of this subspace? So the idea, what's the idea? The idea is actually very simple, because you want the coordinate of the factors that you're interested in satisfy this pair of equation. So let us solve, okay? Let's solve this pair of equation together. So the two equations are x1 minus x2 plus 3x3 equals 0. The another equation is 2x1 plus x2 minus x3 equals 0. Okay? Why do I write in different order? Well, basically because I know I'm going to use Gaussian elimination, and I want this top left-hand entry to be 1. So I do it first, okay? I do it first rather than write down another matrix again. So we are going to solve this system by using Gaussian elimination. So in matrix form, the equation look like this: 1 minus 1, 3, 0, and 2, 1 minus 1, 0. Okay? And then the guy that we want to kill is this guy here. How do we kill this? We simply multiply the first row by minus 2 and add it to the second row. Okay? So we multiply the first row by minus 2 and then add it to the second row. And that will become 1 minus 1, 3, 0. So 1 times minus 2 add to 2, 0. Minus 1 times minus 2 add to 1, and then you get 3. And then 3 times minus 2, and then add to 1, you get minus 7 equals 0. So now you're done because this is already in upper triangular shape, or in aka a row echelon form. Okay? And then the second equation says 3x2 minus 7x3 equals 0. So what does that mean? So how do I solve this equation? Well, either you can say x3 equal t, then solve, then x2 should be 7 over 3t. Okay? So this is one possibility. It's work, okay? It's true. But I hate denominators. So a more convenient way is to take x3 to be 3t. Right? Because then x2 becomes 70. So if you do this, then you don't have any denominator. You don't have to do this. It's not wrong to have denominator, but then I'm just lazy, okay? I'm just lazy. That's why I take this pair. And then after solving x2 and x3, how do I find x1? x1 comes from the first equation. The first equation says x1 minus x2 plus 3x3 equals 0. So I have x1 minus 7t, and then plus 3 times 3t equals 0. So x1 turns out to be minus 2t. So hence, what are the solutions to this equation? The solutions are, so phi turns out to be, to satisfy this pair of equation, is the same as taking x1 to be minus 2t, x2 to be 7t, and x3 to be 3t. And then, of course, you can take our common factor t from each entry. So minus 2, 7, 3. And what is this? This really just span of minus 2, 7, 3. And because I've only one factor, and that is non-zero, so this must be itself linearly independent. So this form a basis. So hence, minus 2, 7, 3 is the basis for phi. Okay, it's a basis for phi. And because my basis has only one factor, that means that the dimension, so the dimension of phi is just 1. The number of factors in your basis, okay, is 1. Okay, this is a 1. And that's it. Okay, so this is a application of Gaussian elimination to solve problems that we discussed last time. So last time we did discover equation basically by inspection, but Gaussian elimination gives us a more systematic way in resolving a basis for a subspace.